So you have the data? So you're working? Yeah, so don't worry about it. If you've already started on Swivel and you got your data and then Swivel's down, just check before the assignment's due to see if you can get it. But speaking of which, I have extended the deadline because of all the issues we've had with Swivel. So it's now, your homework is now due at midnight Wednesday next week. And I spoke with Wayne and Harry yesterday, and they are going to dedicate next week, Tuesday's session to if you bring what you are thinking of as your final plot and would like to show it to them and get some feedback and a critique, they are happy to do that. So if you want to shoot for having Tuesday, having your sort of rough draft of your graph and caption, they can give you feedback on it. So I'll post an announcement on BSpace about the change in the due date for the homework assignment. Are there any other questions? Today we're going to talk about a certain kind of data which many of you might be using for this homework assignment to come up with your beautiful graph, and that is when one of the quantitative variables that you're using is time. So traditionally, when we have time in another quantitative variable, the plots that we make put time on the horizontal axis. So we think of time sort of marching along on the x-axis. And so we're going to look today at one particular example using time. The other things that we'll be covering today are a comparison of box plots and pie charts, and an investigation of color and how best to use color in plots. All right, so to start with, what we're going to be looking at is data that's collected on the Mauna Loa volcano. This volcano, you can see that tiny dot on the world map that's, excuse me, not that dot, but the big round circle that says Mauna Loa is roughly in the middle of the Pacific. It's on one of the Hawaiian islands, in fact, the island of Hawaii. It's the largest volcano in the world, and it's about 4 kilometers above sea level. Then it's another 5 kilometers or so down to the bottom of the ocean. And because it's so big, there's an indentation. And in fact, from the top all the way down to the bottom, it's 17 kilometers from the base to the top. These pictures and the data that we'll be looking at this morning are from the Scripps Institute and NOAA. So on this volcano, there's an observatory. And at the observatory, they have a continuous collection of, or monitoring of, carbon dioxide. It started in 1958 and is the longest continuous record in the world of carbon dioxide measurements. The carbon dioxide is measured in parts per million. Carbon dioxide is given off by burning of fossil fuels, and it's thought that it could be a factor in global warming. So this is a really important record of how the atmosphere has changed. Because this volcano is at the middle of the Pacific, it's not being affected by the burning of local fossil fuels, and it's very high up as well. And upper safety limit for CO2 is 350 parts per million. From the investigations that I've done on the web, I'm not sure where the 350 parts per million comes from, but that's on the Scripps Institute website. Okay, so here's the data from 1958 to 2010, and the pairs of observations now is the time. This is monthly data, time and carbon dioxide. The monthly data is an average of the measurements for that month. In fact, for this particular data set that I'm showing, they actually averaged the measurements for that month and the 5 previous months. So it's sort of a smoothed monthly average. We don't usually use points when we plot time data, time in carbon dioxide or time in some other numeric variable. Some of you have seen that on Swivel or Many Eyes, they're using bar charts to plot time data. That's even more unusual. More typically, we instead connect the dots so that we can more easily see a time trend. Right now, when we look at this graph of time and carbon dioxide, we do see a trend, but we've got all these plotting characters, plotting symbols being nearly plotted on top of each other. If instead we change the option when we make this plot to connect the points with dots, since we do have a sequence from one to the next, which is not something that we have, for example, with the baby data, it doesn't make sense to connect the dots with the heights of mothers and fathers, because to go from one set of parents to another, there's no connection. Whereas here, the data is in sequence, time order. And so it does make sense to try and connect the dots. And that's what this plot does. Now you can still see the trend, and what else do you see? Yeah, you see these little oscillations, right? Those are the sort of the little seasonal variation in the carbon dioxide. And we can overlay that with the red curve, which is a time trend, which is also available from the NOAA site. I've put a marker in here at 350 parts per million because the Scripps Institute says that that's a particularly important threshold. I put another marker in for 1988 because that's when the carbon dioxide levels at this volcano first exceeded 350 parts per million, and you can see that it has continued to climb from that 1988. Does anybody have any other observations about this data? Does it look linear? What were you going to say? A little bit linear, that's right. But is there a little curve in it as well? And what's that curve telling you about the rate of change? It's getting faster, that's right, it's changing, it's getting bigger. So we're going to talk about perception related to this carbon dioxide plot. And in particular, we mentioned on Monday the aspect ratio. And that's the aspect ratio, remember, is looking at the data region, measuring the height and the width of the data region and taking that ratio, and that's our aspect ratio. And what scientists have determined with experiments with people is that they can most accurately see the rate of change in a plot when the information on a plot is banked at 45 degrees. And we just briefly mentioned what that means at the end of a lecture on Monday. And to review, if we return to our plot, we can, in effect, the sort of the trend line is, and its slope is essentially the banking that we're looking at. And roughly we want that to have a slope of roughly 1 or a 45-degree angle. Banking in general means if we look at these little line segments that are connecting points, that roughly we want the orientation of them. If we look at that as a whole collection of data, of orientations in positive absolute value, that we roughly want the center of those orientations to be about 45 degrees. And so that's what this plot achieves. Okay? Now, we're going to do a little aside and talk about global warming a tiny bit. In 1981, the U.S. Senate convened scientists for testimony about global warming. And at that time, Al Gore was a U.S. Senator, and he produced the data from the Mauna Loa observations. And at that time, they had only seen the data from 1958 to 1981. So let's back up and take a look at that. So we hadn't even gotten to the 1988 threshold passing of 350 parts per million. We're down here at about 1981, but you can still see that there was a climb in the amount of carbon dioxide that was being measured at the volcano. But roughly, if you were to only zoom in on 1958 to 1981, you'd still see this upward trend. Sorry, I'm moving a little fast. Okay. So a scientist, Pewitt, who was a witness for the Department of Energy, said that he thought that Gore's plot was very misleading. He said it was very misleading because it didn't include zero on it. And if you remember from Howard Wehner's Dirty Dozen that we talked about on Friday, we did note that at times you do want to include zero, or you want to, or at a minimum you want to include a scale on your vertical axis so that you can judge the size of an effect. And so there's a difference between being able to judge the size of an effect or including zero. And Pewitt was claiming that if you didn't have zero, you couldn't judge the size of the effect. And so he called it chartology, what Gore was doing. So he said, this is a quote, "It is a clever piece of chartology because it can be read the wrong way." He went on to say it's intellectually just exactly correct. So in other words, there's no misinformation. All the data were correct and plotted at the proper place. It displays 315 going to 336. At that point in 1981, the highest measurement was probably 336, but it appears to be going from zero to very large amounts. So he's claiming that because zero is not on the y-axis, people automatically are thinking that it's on the y-axis and thinking that this is the trend upwards. There's Stephen Schneider, who's the author of Global Warming. This conversation is excerpted from that book, and essentially he called Pewitt's objection to Gore's plot as double talk. So I'm going to turn it over to you and ask, why do you think he's calling that double talk? Yes, Adrian? Mm-hmm. Yeah, essentially the main point is that you're going to look at the y-axis to see where it started and where it's heading to, and you don't need to always have zero on it. Zero is actually not even meaningful in this case. It's not that we would ever necessarily have zero levels for carbon dioxide. That's right, and as you were saying, the 350 is a benchmark value that we care about, not necessarily zero. So we're going to go on to take a look at, if we were to include zero on this plot, what would we need? How would the graph change? So I have two plots here. One's a very narrow, tall one, and the other is a very wide, squat one. The narrow, tall one I've made in order to bank at 45 degrees. So if we go by that principle of banking at 45 degrees, I need to have a very narrow plot and very tall if I'm also going to include zero. So one of the points I'm trying to make is that some of the things to not do when you're graphing, that Howard Wehner's Dirty Dozen or other ways of having clear vision and clear understanding, they don't always go hand in hand together. Sometimes they're problematic, and you have to kind of choose between, shall I bank at 45 degrees or should I include zero, and which is the most important feature or that I want to try and get out from my data. In this particular one, well, I'll ask you to give me some comments. What do you think about this narrow, tall plot? Yeah?
I think one of the points in the meeting was that the data should fill the entire space.
That's right.
And so that doesn't do that.
It surely doesn't do that. One of the points that we try to do is to have the data fill the entire data region. Clearly it's not. It's only in the top quarter or so of the data region. And so there's all of this empty space, which is just wasted space. It also makes it hard for us to see that sort of seasonality that we saw before. Now that's not the most important feature. The most important feature is this sort of linear yet still a little bit increasing trend in the carbon dioxide. Now, so if we try to fill the space more, we wind up stretching the plot out. And you can do this in R really easily by simply taking the plotting window and taking one of the corners and moving it around to reshape your plot. What happens now here in the bottom plot is it looks like now what's the banking is almost flat. It's nearly zero. So it's really hard for you to judge that this is even increasing. It looks like, well, maybe it's slightly increasing. But you don't see the fact that it's increasing even faster as time goes on. And it's hard to even see that we've passed the threshold of 350 parts per million. So here, when we're struggling between filling the data region, including zero, and banking at 45 degrees, I would opt for the plot that I already made earlier, which is one that banks at 45 degrees and fills the data region, and therefore does not include zero. Okay? So there have been, I started talking to you at the beginning of the semester saying there have been tremendous changes in statistics in the past 10, 20 years, a lot having to do with the advances in computing. Some of those you're struggling with right now for your second homework assignment. And one that's come up just in the past 5 years or so is Gapminder, which was developed by Hans Rosling, a professor in Sweden. And essentially what he says that he wants to do is liberate the x-axis from time, or from the burden of time. So for years and years and years, whenever we have time, just like what we just looked at with the carbon dioxide plot, that has always gone on the x-axis. Now with new media, he's developed a technique where he puts time in the time domain. And that means he's creating plots that are not static plots. So I'd just like to show you, here's the URL. So if you want to cut and paste it out of my PowerPoint, you can. Or even better, you can go to the web, go to Gapminder, and I did a search on carbon dioxide, and they, in fact, have a plot. I'm going to move this over and try to make it just a little bigger for you to see. Oh, I guess it's not going to get any bigger. The plot itself is not going to get bigger. So, and I'm going to hit the play button. So before I hit the play button, I want you to just sort of, because it goes pretty quickly, I want to point out a few features here. It might be hard for you to read some of these things. I can't even read them from the front. The x-axis here now is income per person. The vertical axis is carbon dioxide emissions, tons per person. So it's a per person emissions. There's a little map of the world where the continents are, or roughly, are different parts of the world that have different colors. And those are going to correspond to the circles. There's going to be a circle for every country that has some significant amount of carbon dioxide emissions. Starting in 1820, there weren't very many countries emitting carbon dioxide. Do you have a guess as to which country is the one sort of large circle here? The UK. So if you put your mouse over it, it should pop up as the UK. I'm not sure why it's not. Now I'm going to hit the play button, and what you're going to see is you're going to see it going through decade to decade. And the UK's carbon dioxide emissions is going to be move to the new point in the new decade according to income and emissions per person. And the circles are going to increase in size as well. It doesn't say, oh yes it does. This bottom right tells you how the circle size is being determined, and it's the yearly carbon dioxide emissions. So the size of the circle, the area of the circle. So these guys have done a very good job. One of the other Howard Weiner Dirty Dozens, remember, was if you scale, if your measurement is linear and you represent it with something that's got area. In this case, they have the area corresponding to the carbon dioxide emissions for that year. And so we're going to be, so how many variables are going to be represented here? Yes? Three, what are they? Income? Emissions per person? Time? There are actually two more. There's countries, because every plot has in fact, there might be three more. Every plot has if you move your mouse over it, you can see what country it belongs to. What else?
Yearly CO2 emissions.
The size, the area of the circle is another variable. That's the yearly consumption, or emission, of carbon dioxide. And one more. Color. What's the color represent? Continent or area in the world. So in fact, he's got 6 pieces of information on this, in this, I'll call it plot in quotes, because without the animation, you don't actually see one of the variables. So in a way, similar to Menard, if we went back and looked at Menard's Napoleon March, he also had 6 variables in his plot. So here we go. Here's the, oh, come on, there we go. So you see the UK just bumping up, going really quickly. Do you see there's one yellow dot? Guess what yellow dot that country, that's right, that's, there it goes. In 1900, it gets really big. And now there's a little blue dot coming along. Here's a red dot that just got really big. And there's another red dot. What do you think those 2 red dots are? China is one. What's the other one? One's Australia, right? So notice that they say here that on the side, they say that the amount, you can't see it here, the emissions per person in the United States is about 20 tons. And in China, it's only about 4.5 tons per person per year. Yes? Yes, you can. There are so many options you can do. You can choose a subset of countries. You can focus in on one country and trace it through time. So if I click on one of these countries, oh, there you saw it there, the country title. But there's a way to also track it through time, which I'm having trouble doing. But you can do all sorts of things. So I encourage you to go there and play with it and see the kinds of things. This guy is a professor at Sweden, and he developed this because he said his students weren't getting it. And so he came up with this approach to teaching about sort of global statistics in a way that he thought his college students could better understand. I've posted an article on our BSpace site called Liberating the X-Axis from the Burden of Time, if you care to take a look at it. Okay, let's get back to the lecture. There's Gapminder. That's the URL. Yes?
I was just curious, on that graph during the time, there were dots that could go off the top.
Yeah. Oh, did they go off the top? I know they're very erratic. So I've actually spent some time trying to figure out what's going on there. I believe that some of the data might not be as clean as as you would like. And therefore, some of the really erratic motions of those plots, I think, are because there's missing data. And I haven't seen them go off the top, but I have seen them move drastically from low values to high values and back down. And my thought is that that's because, for example, the data might only be reported every 5 or 10 years, and they are marching through the animation in a yearly basis. All right. It says pop quiz. I'd like you to all get a fresh piece of paper and number it from 1 to 6, like that, in column 1, 2, 3, 4, 5, 6. You don't have to put your name on it. But don't look at your neighbor's piece of paper as you answer these 6 questions. Okay? First question. Compare the blue vertical bar to the white vertical bar. Answer, write down a percentage. What percentage of the white is the blue? So just to make sure we all understand each other, if they were exactly the same height, the blue would be 100% of the white. Okay? If it was half the size, it would be 50% of the white. So what percentage of the white is the blue? Write your number down. You ready? Next one. Number 2. What percent of the white is the blue? Same question. So if the chart pie was split exactly in half, the blue would be 100% of the white. What percent of the white is the blue? Ready for the next one? What percent of the white is the blue? Write your percentage between 0 and 100 down for this one. Ready? What percent of the white is the blue? This is number 4. You got 2 more to go. Okay, number 5. What percent of the white is the blue? Do you get there's a pattern here in the questions? Next one. What percent of the white is the blue? This is your last final question. All right, now what I want you to do is your paper is going to be graded by someone else. So I want you to trade papers, hand your paper to someone else. How about you right here? You too. Did everybody get to swap with someone? Yes? All right, so here we go. I want to know how accurate you are, and I want someone else to judge how accurate you were. So you've got your column of guesses. Here are mine. Mine are slightly unfair because I actually knew what percent the white the blue was of the white. There's the truth. So next to their numbers, write the truth, just like I have done. The first one's 65. The second is 35. The third is 60. Fourth is 75. The fifth is 30. And the last one's 75. Then what I want you to do is take the absolute error. In other words, 70 minus 65 is 5. If you have a negative number, turn it positive. 33 minus 35 is negative 2. Make it 2. Do that for your neighbor's numbers. Yes? The truth, you mean? It's a percent of the white. You guys weren't paying attention. That's why I gave you those examples. When they're the same size, it's 100%. All right, what I'd now like you to do, notice on right next to those, the kind of chart you were looking at. Bar, pi, pi, bar, bar, pi. Now talk amongst yourselves for a minute to see, do you see any difference? Are the errors roughly the same? Compare yours with your partner's, whatever groups of 2 or 3, and say, do you have the same size errors, whether it's pie charts or bar charts? And some of you, if you've done it really incorrectly, are going to have a hard time doing that. Why don't you come over and talk to these guys? So he's sort of screwed up his things, right? Oh.
There is no way there was that 75% of there anywhere.
Why do you say that? It's clearly very close to 100%. It's what proportion of the blue is the white.
So if you put the blue inside the white, how much is blue?
Yeah, if you put the blue inside the white, oh.
That's so confusing, though.
That's the point. That's exactly the point. Yes? How is this? Okay, guys. So I think the fact that you're confused by this.
Well, it just shows us like that this is a bad idea.
And that's why pie charts are bad ideas. Yes. It says essentially if you take the blue and stick it inside the white, does it fill it up? No, it fills up roughly 3/4 of that area. Oh, yeah. So if it were exactly cut across the middle, it would be 100%. What percent of the white is the blue? I think a lot of people screwed it up. Is that right? All right. Let's regroup. How many people screwed it up? Wow. Okay. I think this makes the point very, very well. The point is that lots of times when we're making these charts, what we want to do is make comparisons. We want to compare one group to another group. So you probably had no problem getting these right, the bar charts, or getting pretty close to right. Because you were saying, oh, look, the blue, whatever category that is roughly 1/4 or 1/3 or something like that of the white. That's really important comparison that you're making. When you make a pie chart, it's hard to make that comparison. And in fact, you're not even making that. It doesn't even, to a lot of you, it doesn't even make sense to make that comparison. So it's one thing to say, oh, with a pie chart to say, oh, look, the blue is roughly 40% of the total. That's the kind of comparison that comes naturally when you make a pie chart. So if you want to see how much of the total does the blue occupy, sure, pie charts are fine. But if you want to be comparing groups, pie charts don't cut it. So we had an in-class impromptu quiz experiment here, and it shows how important it is to get the experimental conditions right. So we failed miserably because a lot of you, at least half of you, didn't even get how to do the problem. Our next topic, starting next week, is going to be about design of experiments. We could use this as an example of what you have to be careful when you design experiments. So Cleveland, who is the author of the first chapter that you're reading about visualization and making charts, has done several experiments with people's perception of plots. And in particular, he did this exact comparison. He took about 50 subjects. He gave them all 40 different plots, some by bar charts, some pie charts, and asked that exact same question. What percent of the white is the blue? And there's the true percent across the bottom. These are the results he got. He has the log in base 2 of the absolute error. And the left plot is for pie charts, where you have to use angles. The right one is for position, meaning you're using the heights, the position along the line. And notice that there are errors in both. But we see that when there's a pie chart, when we get past about 35% or so, the errors start to grow. And until we get to where they're nearly 50-50, or in other words, one is 100% of the other, we've got pretty large errors. There's a different plot of this in that chapter, the reading for this week. So take a look at it and see. But the moral of the story, I think we've seen here in class already, is that pie chart judgments are far less accurate than bar chart judgments if the kind of judgment that you're trying to make is a comparison across groups. Pie charts, errors tend to be much larger for anything greater than about 35%. Whereas the bar chart errors tend to be about the same size no matter what the percentage is. Okay, let's move on to talk about color. So far we haven't really been paying too much attention to color. We know in R we can use color names in quotes like red, green, blue. There are all sorts of fancy names. You could use cornflower blue, for example. That's what I use to make those pie charts. There's pink and bright orange, and there's all sorts of names. But choosing the right kind of colors for a plot can be really difficult. You saw that really ugly plot I made that had filled in the underneath the curve with an orange. If you'd seen it on my computer, it was even far uglier. And that's because the background was a very, very bright pink. So when we projected it through the LCD projector, it became a very washed out pink. So one thing to be concerned about is the medium on which you're presenting your information. You want to be able to check is it printed on paper, is it on a computer screen, is it being projected through an LCD projector. That might affect the colors that you choose. Choosing colors is really hard. It's very challenging. Not all of us have that sense of knowing what colors work well together. So I'm going to give you a few guidelines and then tell you that there are someone, a professor at Penn State, has done an excellent job of creating different color schemes. And those are available to you in R if you would like to use them. So one thing is, I've made plots already where I've had red lines and green lines, and 7 to 10% of all males are red-green colorblind. They have a real hard time telling the difference between red and green. So look at this circle. Have you guys seen this kind of circle before? This is sort of like a colorblind test. And whether or not you can see the number in the circle, I'm not going to put anybody on the spot, but there might be a few people in this class who cannot see the number inside that circle because of this red-green colorblind. Okay? Then there's a few notions about color which we'll get into, not a lot. These things are things that are intuitive. One is sort of very colorful or saturated colors. They are hard to look at for a really long time. And you can have this sort of after effect where it's like you see all black or sparks or whatever. And if you want someone to be studying your plot, using really saturated colors is not a good idea. They can't really look at them for a long time. Again, on my screen, this green is very saturated, very bright. It's sort of, whereas this other is a color here in the lower right is a much more subdued color that's easier to look at for a long time. So be aware of that aspect of color. Another is luminance. That can be, if you are looking at areas and you want to be comparing areas, such as with I keep saying pie charts, the pie charts or the bar charts. Lighter colors, this is something people know about in fashion, that lighter colors tend to make things look larger and darker colors look smaller. So if you take a look at these two blocks that I've made, these two rectangles I've filled in R, do they appear to be the same size?
Yeah.
They do? Okay. For some people, the black one appears to be smaller than the light gray one. They are exactly the same size. How do you choose colors? This gets all the way back to one of the very early things that we've talked about. It depends on the kind of data you have. If you have qualitative data, then when you're making plots, you want to be able to distinguish between the different categories or factors. So you want colors such that it's really easy to look and see, oh, that belongs to that group and that belongs to that other group. So you need colors that are easy to distinguish. On the other hand, if you have quantitative data and you care about how high a particular value is, then you want colors such that low values are very faint or light and the high values are quite dark. Sometimes, though, you've got quantitative data and you care about really high values and really low values. And the middle ones are not so interesting. In that case, you want the middle values to be a light color and the two extremes to be dark but not the same color so that you can distinguish between them. An example is might be an election map that you're making and you care about the percentage of vote for a particular candidate. And there's where this notion of diverging makes sense, because you want to see where did this candidate get a lot of votes and where did this candidate get very few votes. And then in the middle ground is less interesting. Cindy Brewer is the professor at Penn State who's come up with a whole set of palettes for you to use in making plots. She's got many. If you do a Google search and find her website, she's got a whole slew of palettes, far more than what are available in R. These are available in a package in R called R Color Brewer. These are the qualitative palettes that are available. And so if you look across a row, those are sets of colors that are similar to each other, yet if you were to use them as plotting colors for plotting symbols, it would be really easy to tell them apart. Here's a diverging palette, which again says the medium values, I'm plotting with quantitative data, and the medium values I don't care so much about. It's the extremes. And I want to know when I've got really low values and really high values. If you take a look at just the top one, it's called spectral, and it has a very dark red for the one end of the extreme and a very dark purple at the other end. And there are all sorts of other things in between. There's purple-orange is the fourth one from the bottom. These are the names of them in R. And this is the sequential palette where moving from low to high, you are just care about where are the high values. So all the low ones are washed out and the high ones are dark. Okay? I have remade a plot that we've looked at in an earlier lecture. This one on the top is the one I made for the percentage voter registration being Democrat, Republican, other, or declined to state. That's when I just used the traditional colors in R, red, blue, green, and black. And I've remade the plot on the bottom using Cindy Brewer's color set 1 for qualitative because I just want to be able to distinguish the parties. So I still have a blue and red. That's why I chose that particular palette because I like the fact that it still had a blue and a red, but they're not the same kind of blue and red. They're not quite as colorful as the blue and red on the top. And then I made the decline to state this purple and other as the green. So I kept the blue, red, and green, and I gave a color of purple that used to be black. So can you see the difference between them? How the colors on the bottom are easier to look at? And you can also really easily distinguish between them. Just briefly, here's the code that you might want to use to create that. It will be posted on the website. So it's a separate package called R Color Brewer. And there's a little, you have to call a function to get the colors. So you load the library, R Color Brewer, and then you pick which palette you want and how many colors you want from the palette. So you call the function brewer.pal. You say, how many colors do you want? 9. And what's the name of the palette? Set 1. The most number of colors I believe a palette has might be 11. It's either 9 or 11. And I assign that to the variable colors. Now, colors is a whole vector. And tomorrow you're going to be learning about how do I pull out a particular single element from a vector or from a data frame. And we'll cover this if we have time at the very end of class. So I'm going and pulling the first color out. That's what the square bracket is doing. And I'm assigning it to a variable called myRed. And then I'm getting the second one, which is myBlue. The third one is myGreen. And the fourth one is myPurple. If we went back to examine the palette, for set 1, it's the third one down. The first color is red, the second's a blue, the third's a kind of green, and the fourth is a purple. So I'm pulling out the names of those colors from her palette. And then I can go and use them in plotting. So I can plot an X by a Y, make it a line type, color equals myBlue. So myBlue now is a vector of length 1 that's got the name of that special blue from Cindy Brewer's set 1 palette. If I were to look at it, say if I type myBlue in, this is the name of that color. It's a weird looking name. So it doesn't have a nice name in English. For those of you who are sort of computer savvy, this is a hexadecimal representation of the color. This is red, green, and blue in base 16. For those of you who don't have a clue what I'm talking about, don't worry about it. It's just the name of the color. Okay? And I was going to show you how to do many eyes. We've run out of time. But I have office hours today in the Student Learning Center from 1 to 2. And I can show you how to download. This particular data set has lots of problems. They've got dashes in there. It's got commas in the numbers. And I found it was far easier to load it into Excel and then use some of the properties in Excel to turn the dashes to NAs to get rid of the commas and then load it into R. All right. I'll see you all on Friday.